And hi, everyone. Yeah, you're very welcome to the talk. So I gave kind of a version of this at Kaggle where we went into the theory quite a bit, and it was a bit more hand wavy around the code. So this one, though, it's it's a smaller group. It should be more informal, and it's Python Ireland, right? So we want to get into a bit of code and show you actually practically how to get started doing some optimization if you haven't come across it before. So that's the idea. So hope you enjoy it. Obviously in better times we'll be together in some kind of a physical space, but in the meantime, just pop questions in as I go, and I'd be glad to answer them to get that bit of interaction. So, okay. Oh, I just need to be able to share a screen, Nicholas. I think you just need to give me access for that.
Yes. Any luck?
I got it now. Lovely. Thanks a lot. Okay, so hopefully you're seeing the presentation here. I'll just see, can I get it moving properly? If for some reason you can't see a presentation, just Nicholas or somebody shout out, or others I presume it's all fine. So just a little bit of background about myself and where I'm working. So I'm in a company called Last Mile Artificial Intelligence. And sorry, just give me 1 second. Sorry, just a bit of noise there. Just gonna close the door.
John, we have your notes as well, the side notes.
Oh, I think you're seeing the wrong one. Okay, sorry.
It's fair, but we have the spoilers.
You got the spoilers. Oh no, I need to keep a bit of suspense here. Give me 1 sec. I'll try that again. Stop sharing. Oh, okay, this has become screen one. Okay. That's what happens when you plug your computer out to plug into your TV to watch on TV. Okay. So let me start once more. Okay, hopefully you're seeing the actual slides now. You are. Okay, great. So yeah, so anyone who doesn't know me, my name's John. I'm a data scientist for about 10 years now. I used to call myself something differently, but then of course I rebranded along with everyone else to try and sound a bit cooler. It's a good definition of data scientist. It's a data analyst who lives in California. So I think we all kind of started to kind of jump on this wave a number of years back. A lot of people fell off the wave because they realized actually a life spent munging data is maybe not exactly what they signed up for. But I seem to kind of like it. So myself and a couple of data scientists and engineers form Last Mile. And the idea is, it's a bit like in telecommunications or delivery that there's a last mile problem in AI. So we've all this really cool stuff on the shelf. We've deep learning, we've simulation, we've social graph, all that really cool stuff. But the companies just can't really take advantage of it because they're lacking that little bit of technical expertise to kind of get things up and running properly. So that's kind of the metaphor for Last Mile, that will help people kind of connect, and just kind of really get that last mile and get some value out of the whole thing. So that's just a bit of a plug for what we do. So what we've found, I suppose, over the last kind of couple of years is that everyone wanted machine learning because it's been the cool thing and the very useful thing the last kind of 5 or 10 years. And then deep learning really kind of ramped that up, especially for unstructured data. So for your text and vision. So what tended to happen though is that it became kind of a hammer looking for a nail for an awful lot of companies and an awful lot of projects. So the first thing people kind of thought about was, let's do some supervised machine learning on this, whereas often the answer was something completely different. So sometimes the answer was just get your data together into a data warehouse. Sometimes the answer was make your data queryable using something like Snowflake. Sometimes the answer was just use a spreadsheet. Just really depends. But one gap we found in the last probably couple of years is that an awful lot of problems present actually as optimization problems, and they're not really being recognized as such because the ML kind of fever. So that kind of led me to dust off my optimization studies from back when I did my master's in UCD about 7 years ago. I was kind of lucky enough to do a course in optimization. I know an awful lot of people going through the master system don't. It's much more on machine learning and the programming side. So I started to notice that an awful lot of problems, you could actually represent them as optimizations and get to a really nice solution using tools and mathematics that's been around for, at this stage, kind of 80 years or so. So that was kind of an interesting revelation to me. So that's why I put together this talk and the code, basically just to kind of give Pythonistas who might be familiar with machine learning, probably familiar with pandas and NumPy and stuff like that, but might not have come across optimization. So that's the idea. I don't want to set myself up as the biggest expert in optimization ever. If there's anyone who's gone really deep into this, my hat's off to you. It's like you can get pretty deep. I'm kind of on the journey myself, but I think hopefully what I can show you is where you can actually practically start using the tools and techniques and concepts pretty quickly and get up and running and actually do something like really, really interesting and useful. So that's kind of the idea. That's my get out clause. So it's funny. I think another definition of data scientist was someone who knows more statistics than a programmer and more programming than a statistician. So I kind of rely on that a lot in my work, knowing a reasonable amount about something enough that I can just get it working and get to a solution. Okay, so so just some resources in the slides there. So this will be available. We'll make it available through, I guess, Python Ireland, and you can come to my website at some point if you feel like it, and it'll be sitting there as well. Also, the code for today will be up on GitHub as well. So I'll put the links out, give them to Nicholas to if you want to put them out for anyone who's interested in actually replicating the code examples. So don't worry about taking loads of notes and all that kind of stuff. It'll all be there for you. So just like lots of references. I'll skip over that bit. So the long version of this talk is kind of going into the background. So I'm really interested in the history of AI and computer science. I come from a history and economics background, so I'm not a mathematician or a programmer originally. So I really love that stuff, but your mileage might vary. So there's a kind of a long version which gets into that. We're going to focus today on the actual practice of operations research. All right. So operations research is kind of the field that's been around an awful long time, and optimization is really kind of the core focus of that field. They do lots more things, but at the end of the day, it often comes back to optimization problems and techniques and maths around that. So the two things, optimization and operations research, are almost synonymous in a lot of ways. So just a couple of things. Again, I'll tread lightly over this to get to a bit of code, but one thing just to that got me thinking is, like, where do we actually use analytical methods in business? And I say analytical methods just to keep it fairly generic. So okay, it could be AI, it could be some kind of actuarial stuff, it could be statistics, it could be whatever. So I suppose the interesting thing that I kind of realized, because I'm getting long in the tooth and I've worked with statisticians over the years, is that there's been people doing analytical work with computers in business for a long time. So before data science was a thing. And those people have been called statisticians, operations researchers, lots of different things, analysts and whatnot. So data scientists were kind of, we're kind of Johnny come lately to the party in a way. And there's always that tendency when there's a new field is to kind of ignore everything else that came before you. And that can be kind of healthy, just starting new and get some really interesting ideas. Very healthy in the case of deep learning, because everyone completely wrote it off until Jeffrey Hinton basically revived it, 10 years ago. So very healthy in some ways, but sometimes a nod back to the old traditions actually can be actually really useful. So optimization and operations research really came about during the Second World War. So it was the challenges of production, materials, for military and civilian use. So what do I make? What do I use my steel for? Do I use it for girders for buildings, or do I use it for aircraft, or in what mix? So there was a lot of kind of interesting mathematical problems to solve to optimize production, for example. It did pretty well. Von Neumann got involved, as he does, or as he did with everything, pretty much. The founding of neural nets, also there, the founding of linear programming. So came up with dual theory and lots of different cool stuff. So it kind of took off in the 1950s in the US. So for the American system of manufacturing. So you had these giant conglomerates who were kind of rich enough and innovative enough to basically fund lots of scientists to get their hands dirty and try and solve problems. The Rand Institute in the background kind of doing the various barmy schemes, trying to apply this stuff to the war in Vietnam, and all sorts of odd things happening. So you kind of rise of technocracy in one side, but also the rise of some pretty interesting and useful techniques in business and manufacturing. So it gets kind of starts to get a pretty good run. So what is a linear program? So the idea is that you have some kind of function, some objective that you want to maximize. So the really kind of standard introductory model is the knapsack problem. And this is the 0, 1 or binary version of it, where you're saying, I've got a few items and I want to know which items am I going to put in my knapsack. All right, so each item will have a different value and a different weight. Your constraint will be the total weight of the knapsack, and you got to choose the best combination. So if you have a very small number of items, it's pretty trivial. You can just kind of rearrange the combinations until you get there. But as the number of items increases, or as, say, your constraints get a bit more complex. So say you're in manufacturing and you're saying things like, well, I need a certain proportion of this minimum. I can't use these chemicals in combination because that'd be too volatile. So your rules start to get a bit hectic. Then you get into basically needing some kind of an optimizer under the hood to work through these problems. So the other part I mentioned is that you're going to have some kind of constraints. So in this case, AX less than B. So the weight of the item multiplied by whether it's there or not, so just 1 or 0, sum them up. That's got to be less than the weight of the knapsack. So you can represent it mathematically very simply. So you have that, and you have your maximization, which is going to be the sum of the value. So the sum of C by X. All right, so pretty straightforward. But yeah, computationally, there's no kind of very clear, kind of heuristic way of doing it, procedural way of doing it that isn't NB hard. It gets exponentially, huge as the number of items increase. The other thing is, if you expand this out and say, well, I can have repeats, so I can have any number of items.
Just interrupt you because you take for granted everyone knows what an NP-hard problem is. So can you just quickly?
Oh yeah. So I'd say as computer scientist here, you can probably define it way better than I can. But yeah, basically it means it's not going to be solid in polynomial time. So it's going to be, it's going to be probably something to the power of something else. So as you increase your inputs, your x's in this case, the compute time is just going to explode. So you're not going to have a tractable kind of program that you can just complete in normal time for any significant number of inputs anyway. Yeah. So yeah, thanks for that. So yeah, so it's basically something that you need a clever algorithm under the hood to be able to kind of reduce that solution space and kind of get around the fact that it's NP hard, get around all these different combinations that you don't want to have to kind of sort through. So that's kind of the idea. Just one more thing to say about the whole machine learning kind of paradigm that we're in at the moment is that it's really good at labeling things. So Kazi Korsakoff of Google, who's a big hero of mine for her really kind of succinct, commonsensical descriptions of what's going on in ML. So I highly recommend her stuff. Basically, she calls supervised machine learning a thing labeler, to get rid of the mystique. And that's what it is. So you've got a bunch of data, a bunch of labels, and you learn how to label your data. Now, the problem with that is once you finish labeling everything, Like, what do you actually do with those labels, right? So, and this is a problem that we see kind of again and again in business. So, for example, I've labeled that customer as somebody who might churn, or I've labeled that image as, deforestation potentially. All right, well, what do you actually do about that? That's actually, generally speaking, the much harder problem. And that's generally what people that's the problem people want to solve. So I think I have it here. Yeah, what should I do? Not what do I see? So if you've been reading kind of the data science literature the last kind of decade or so, there's this big thing of like moving from descriptive to predictive analytics. So that's kind of where we are now with machine learning. And then the promise is to move from prescriptive analytics, right? So what should I do? But again, that's kind of difficult because that implies you have to make some kind of a decision, right? So some kind of a decision. And then if you got to make a decision, presumably you got a bunch of different decisions that you could make. So that implies optimization, right? What is the best decision to make, in a particular circumstance with particular data? That's kind of the problem that you're faced with. Now AI, certainly in terms of the machine learning approach, is a fundamental problem with insight and decision making, because what it's always trying to do is basically fit curves and try and map the data to some kind of a labeling without necessarily worrying about all the features of that model. All right, so it's basically parameter free, it's theory free to at least a certain extent, and that's the great power of it and the generalizability of the whole thing. So it's fantastic. But we're getting into this whole situation now where people want explanations. They want XAI, explainable AI. So, and people are trying to do that. So there's some really kind of interesting work going on. There's some great papers. There's some really nice open source software like Eli 5 and SHAP, which is fantastic. But an awful lot of it feels to me like it's trying to close the barn door after the horse is bolted, because you're basically saying, I'm going to make a representation of this problem or this situation, without understanding the features of it or how they're linked together. I'm going to make some kind of a prediction, and then afterwards, like, oh, by the way, why did I make that prediction? Well, fundamentally, there's a problem there, right? Because you were trying to do something without representing all those interactions. So that kind of brings us into this, okay, well, we're faced with these problems of how do we optimize decisions. Now, if you want to optimize a decision, presumably you have to understand the system you're trying to optimize. Because otherwise, how can you justify your decisions? Like, how can you actually explain why you're doing it and weigh up the pros and cons and actually get to a solution? So, yeah, so we're faced with these kind of various problems. So I'm just going to check. Oh, yeah, no questions there. That's fine. So, yeah, so we're faced with these kinds of problems. So the classic one is the traveling salesman problem, which is another of these kind of optimization problems that you're probably familiar with. So it's a classical kind of computer science challenge. Again, it's NP hard. You have to basically kind of sort through all these different possible routes, find out which is the best one, eliminate the ones that don't satisfy your constraints. And ultimately speaking, if you're going to use exhaustive search, it's going to take you forever for a large number of routes. So it's that kind of problem we want to solve. So the first thing that optimization kind of gives us is a way to start representing these kind of optimization problems. So if we just go back to knapsack, if we're, say, going on holidays and we want to be able to take a number of, say, books, sun cream and clothes, so in our knapsack, a really nice way to represent that is a graph. So the edges then are the decisions we make, the number of each of these items we're going to take in our knapsack. So it really becomes a graph problem where you're going to try and find the weights for each edge and the values for each of these edges. And that opens up like all the kind of nice computer science stuff around graphs. So you can have your edge lists, you can have triples, you can have lots of nice ways to represent a graph. And then you can store those coefficients in matrices of whatever shape is necessary, and then be able to start to work with that data in a program. So you're kind of starting to represent the problem, and that's a good step in helping to get to a way of starting to solve the problem. So you have this kind of nice data representation here. Another thing as well is if you start thinking about all the different combinations all the different decisions you could make, that they kind of form a graph as well. So you can have all these different combinations of decisions which kind of form the major decision you're going to make. So what happens is that it turns into kind of a search problem to find the best path, right? So if you could in some way kind of, you know, filter out some of these branches where you know you're not going to find a great answer on those patches, well then, you know, your problem's going to become much, much more tractable, right? And that's actually the way that some of the algorithms start to work, actually. So I'm just going to check the questions here. Oh yeah, good question there. Yeah, just remind you of anything. Someone asked, what is it supposed to remind us of? That's a great question. I skipped a few slides because, you know, I'm not gonna kind of rabbit on too much and get to the code. I think the bit I was missing there is that, yeah, what does it remind me of? Well, it's basically neural networks, because if you think back to neural networks, it's basically loads of matrix manipulation and multiplication, linear algebra, right? So once you kind of start to get this stuff into matrices and be able to manipulate it, you know, you're basically kind of into the same kind of maths and same kind of programming. Also, von Neumann is just there for the birth of both of these things, as he was for everything. So, yeah. So yeah, great question. That was kind of the trail of breadcrumbs I think that I was kind of trying to lay out there, but missing quite a few breadcrumbs because this is the shorter version. So yeah, thanks for that. So yeah, so if we just forget about trying to be clever for a moment with the you know, getting rid of the different branches, if we just say, you know, feck it, let's just look at all the different, you know, combinations here and just try and solve it. You know, well, there's ways of doing that. There's ways of doing that. So let's just have a quick look some of those. So this is where I skipped the code, so things will probably start to go horribly wrong. If you can't see this, you know, Nicholas or anyone, just let me know. But otherwise, I presume you can see the screen okay. So you should be seeing VS Code here. You know, kind of my current IDE seems to work quite nicely. Kind of strange that Mr. Gates is so involved in the open source community, but you know, that's okay. So the first way we can basically try and solve this is just generate all those different combinations. And then post hoc, just say, okay, well, which of these combinations satisfy, you know, the constraints, and then, you know, which is the best, right? So this is what we've done here in this program. And the nice thing about it is we only need NumPy and pandas. Actually, we don't even need pandas. It's just to kind of give a nice visual representation. And actually, you could do it without NumPy either, but it's kind of handy just for the matrix. So you have NumPy and pandas. There's no, you know, no deep software kind of going on there. And really, so yeah, we set up the problem here. So say in this case, our items are Suncreen books and clothes. And the value of each of these that we ascribe to each, say 10, 3, and 1, right? So we really want our Suncreen on holidays. Now, an interesting thing about these is, you might ask, is how do we get to these value weights? And actually, that's a big part of the business analysis that you'll do in these problems when you meet these problems. Sometimes it's a very obvious dollar amount, but other times you are mixing different measures, and you have to come up with some kind of utility that you can apply, you know, across the different things. So let's call this kind of an enjoyment utility measure in our case. So we ascribe these values at 10, 3, and 1, and the weights are more straightforward. So say 10, 3, and 2 for these items. And the capacity of the rucksack or suitcase is 12, right? So yeah, so basically our constraints are pretty handy. We're just saying our total weight has to be less than the capacity. Yes, the total weight we're going to generate with our items has to be less than capacity. So all we really need to do to set up the problem is just generate the different combinations that are possible of these three things. So here's an algorithm to do that. So basically it just generates a sequence of 0 and 1 combinations, of possible combinations, up to n, so up to 3 in our case. So if you just run that through, you can see that matrix there. So Suncreen books and clothes. So these are the different combinations that are possible, right? You can take all of them, you can take 1, you can take 2, whatever it is. So you can see that you can just kind of quite easily generate these combinations. The code I've used to do it here is basically kind of the way I do it on a whiteboard. I'm just kind of, taking a line of zeros and I'm just changing one at a time, changing this one to 1, changing the next column to 1, and just kind of copying it out like that. And that generates this.
Sorry, John, I can't ask a question in the proper channel, but why didn't you use ITER tools combinations to generate that?
Yeah, you totally can. You totally can. So here's another version of it here, actually. Basically.
Oh, sorry, I just disappeared again.
No, it's a great question. It's great because it set me up quite nicely. So it's great I did have an answer for it. No, thanks, Nicholas. Yeah, so yeah, you can do it. You can do it very quickly. So you can do kind of an iteration here. So Sean, who works with me and is like much more of a software engineer than I am, basically did the whole thing in a one-liner there. I just kind of like to see the mechanics and see how things play out, and and see all the different steps. But yes, you can do this very, very, very easily, especially for binary problems, right? So you can use this kind of bin thing here. If it's unbounded knapsack where you can have more than one item, then you need to generate base to the 2 or 3 or 4 kind of thing. There's some nice code out there which you can steal to do that. So you can really kind of do the same thing. So yeah, that just generates your kind of potential solutions here. Let's call it the base matrix. And then really all you have to do then is just multiply your weights, and get your total weight for each combination, get your total value. Run your query to kind of get rid of all the non-feasible ones where your weight would go over your allowed, and then just get the largest, just get the one with the best total value there. So it comes out of this one here. So looks to be 1 sun cream, no books, 5 clothes. So a completely hedonistic holiday, no reading, just get on with it. So that's kind of the idea there. So I suppose just to show you that you can solve these things with brute force just by enumerating the combinations or permutations, and then just constraining it, and then getting your max or your min or whatever you want to get. Right. So there's nice ways of doing it. Now, if you're a bit more of a CS head, what you'll probably realize though is that you don't necessarily need to do the computations to enumerate all these different computations. So there's a really nice concept called dynamic programming, which you might have come across, which I'm not going to go into in detail. It's probably kind of a half an hour, presentation on its own, if you haven't come across it. So I do some links here to kind of nice explanations and stuff. But basically, it's a tabulation method. It's a nice heuristic. Again, it's something you can do in a whiteboard, which I love, and you can actually you can write out all the different combinations, and then use this neat little algorithm to just kind of track back through the cells and find the optimal solution. So it's an iterative kind of heuristic way of achieving it, and it's very, very handy. Yeah, really, really good from Abraham. Yeah, memoization is another nice way of doing it. So for dynamic programming, if you like recursion, you can do a recursive version of it. And actually, I've got an example to show you in a second. And it's much more elegant, actually, programmatically. It's fewer lines of code, and you can memoize it to basically reduce the memory footprint. So yeah, there's a few different ways of approaching dynamic programming. If you're like me, I think because I kind of come as a gentleman coder to try and kind of say, well, a bit like a gentleman farmer who farms in the weekends. Like I do a fair bit of coding, but it's not my primary thing. And I always find that recursion starts to get really messy, especially when you start to add business logic. So I find it becomes a bit difficult. So I generally will I'll go for a loop if I can get away with it. But both methods are the same, and they run in the same order of complexity. I think it's just a different way of getting to the same thing. But you may prefer that as an option. So the nice thing about the tabulation, or about dynamic programming, whichever method you use, is it starts to reduce the order of complexity quite a lot, because it's basically not repeating some of these interim kind of calculations of weight and value along the way. right? So it's definitely a really nice solution to these things. And again, if your problem is tractable, it's a perfectly cromulent way to do it, as they used to say in The Simpsons. It's a perfectly acceptable way of achieving your goal. You're doing brute force search, but you've made it computationally much more tractable. And that is really important in business applications or in any application, because like more and more these days, we have these kind of things running behind web apps. So people expect them to run either in real time or near real time. You know, so maybe a minute, 2 minutes, 3 minutes is allowable. Sometimes longer. Like you can get away with optimizations that take 30 minutes, an hour in enterprise applications, because people kind of know that's the expectation. So they're used to, you know, their previous software did it in 12 hours on a batch. So now if they can set off a job in the background that takes half an hour, that's absolutely fine. But it does mean that performance is a really critical aspect of the program design for this. So dynamic programming kind of gets you a step along the way there. Okay, so just going back to the presentation for a minute. So yeah, you can start to do kind of some clever things kind of coming at it from the computer science angle. But you know, there's more I think you need to do. There's more you need to do, and that's where linear programming is kind of, things like that are going to help us out. So just kind of a quick note on kind of, say, Kaggle style ML versus optimization. One of the big differences you're going to see is that when you do an optimization problem, you're going to have multiple tables. And when I say table, I kind of mean like multiple entities, three, you know, with different. Okay, yeah. So, yeah, question there. Yeah. So we're going to get on to a few different approaches as well. Yeah. So don't worry, Eric. There'll be a few things for you to get your teeth into. So one of the aspects is that multiple tables generally represent different aspects of the problem with different granularity. So you'll find in a business problem that requires optimization that's very much the way you can represent the problem. Whereas in a machine learning model, we're generally trying to kind of coerce the data into a single table, which will then feed into the algorithm, come out the other end. The other aspect of it is that, generally speaking, we have much more parsimonious use of data and optimization. So the complexity of the problem doesn't depend so much on the size of the input data. It depends much more on the constraints and the objective function. So on the actual problem you're trying to solve. So big data doesn't necessarily translate into big optimization problems. Small data with complex constraints will translate into it. Okay. So to take just to kind of develop a problem a bit more. So if you have your various items you can take on holidays, so say your sun cream, books, and clothes, the first thing you want to do is assign an enjoyment metric to it, or some kind of metric that allows you to rate, you know, whether or not you want to take those things. Your constraints in this case, you might add to them. So you might have a total weight in your knapsack. You might also have, say, a max or min number of the various things you want to take. Also, what you might find is that, say, items are not, you know, generated equally. So in our case, maybe you want to start subdividing books into, say, light and heavy reading or something like that. And you might find that for your holiday, okay, you might have a higher enjoyment metric, say, for thrillers and romances than you have for literature, for example. Right, so you kind of need to go through this business analysis process to figure out exactly what the entities are that you need to discover and include in your model. Okay, so that might get us to kind of a slightly richer data representation as well. Okay, so the mathematical model in this case is then quite simple. So basically, it's again, our constraints are listed there in terms of our min and maxes. And then our sum can't go over the total allowance. Right. If we want to start representing these kind of sub items in a graph, so for example, beach reads and literature make up books, well then we can again represent that mathematically. So we can just say, in this case, for example, that the X4 and X5, so the numbers of these types of books make up the books section. So again, we can represent that mathematically and encode that into the model. Right. Okay, so one thing to say about how the optimization software works is it's very similar to kind of everything these days in Python and beyond. It's a really multi-layer model. So generally we have kind of 3 layers to this stuff. we write our program in Python as usual. We have some kind of an AMPL, a mathematical programming language, to represent the mathematical model in mathematical terms. And then we have a solver under the hood, which will actually churn through and do the work. So if you're coming from the ML background, think like Python, maybe TensorFlow for the framework, and then Atom under the hood is the kind of doing the heavy computational work. The main issue that we have in optimization software, in my experience, is debugging. So the translation of errors between those different layers is often very problematic. And this is where kind of some of the really, the heavy commercial solvers like Cplex can come into their own for production software because they're pretty good at cascading errors back through the stack. And if you get an error in Google OR or some of the open source software, generally speaking, it's going to say something like infeasible problem, or constraints cannot be satisfied, but with not that much of a clue as to where that problem is. So one of the ways you can get around that is in your data processing, have really good test cases around your data processing and setup before you pass the data into the AMPL and through onto the solver. Right, so that can save an awful lot of pain. Often it's just something really silly in the data inputs that was unintentional, but it's basically a silent killer at the end of the day. All right, so that's kind of the framework. Obviously, on the positive side, it just means we have very high level, very nice software where we can basically think through the problem, represent it without getting too deep into the nuts and bolts. Okay, so just to show you a bit of that. So, okay. Okay, so this one here is basically taking this problem, which is now not a binary problem anymore. It's unbounded, as we say. So basically, you can have between 1 and some arbitrary number of each item in your knapsack. And so one really nice way to solve this is to use OR tools, so Google OR tools, which they've just kind of created internally, like a lot of their products, they made available over the last couple of years. So it allows you to start setting up these problems in a very Pythonic way. So you can set up your input parameters here as lists or NumPy arrays. So again, we have our value and weight here. And we can start to use backend solvers like SCIP. And what this is doing is it's solving what's called a mixed integer programming problem. And that means that some of the decision variables and things that we're using are integer rather than continuous. So traditional linear programming is on continuous data. So for discrete, we switch to basically mixed integer programming, or mixed integer linear programming, as it's sometimes called. So it allows for making these discrete decisions. So you can start to use one of the MILP solvers from Google OR, like SCIP. So there's a good range of them you can use. Actually, there's usually 2 or 3 alternatives for each problem you have. Basically, you set up a solver here. So we're basically saying that in our case, it's integer values and they're non-negative for each of these things. Then we set up our constraints here. So we're calling the API here. So we start to use kind of the API parameter language here. So we can do that. We can still refer to our Python variables here, which is quite nice. And when you move to things like PYOMO and some of the other software, they have very kind of specific idiosyncratic ways of encoding constraints with their own kind of mini language inside the AMPL. And the Google OR is really kind of nice and intuitive. So basically, you're just kind of using something you could use in NumPy or in open code, basically. So you kind of encode your constraints here, adding them to your solver, which you declared. When you get into the summation function, this is very specific to the API. So for example, you can't just say I want to maximize a mean, for example. It's not going to work. So you do need to dig into the API to see what are the legal arguments here to generate your objective function. And you will find that there are some idiosyncrasies around that. But for most problems tend to be usually kind of summing over some kind of a matrix, multiplying it or doing some operations on it, mixing the decision variables with some Python variables, like parameters that you have at runtime. and those problems you can represent basically in this kind of way. So that's the function there. Yeah, so basically the rest is mainly just trying to, on the reverse end of the API, just trying to kind of pull out the solution and the variables, and kind of, you know, just kind of get your head around the class structure of what's coming back to be able to see the solution there. Okay, so we can run this through, and there you go. So it runs through quite nicely. So that's Google OR. So the nice thing about it again is you can represent your data and your business problem using the common tools. You know, you can do your ETL, get everything into place, and then put it into your entities, and then populate your constraints and your objective function that way. So that's kind of one way of doing it. Now, you might hit a problem though. So I'm going to show you kind of an extension to the problem here. So one of the issues that you might have is your problem might need to be represented as something nonlinear. So that can happen quite easily. So in our kind of holiday case, what we could say is that maybe, you know, books and sun cream are actually not independent variables, right? So basically your equation is nonlinear, right? Because they're not independent. There's some dependency between these things. So you might represent that value function now maybe as multiplying the value you get from sun cream multiplied by the value you're getting from books, right? So it's kind of a naive representation of it, but basically you're going to have some nonlinear function with those variables. So basically you're expanding your objective function now to say, okay, let's look at all the value we're getting from these various items, plus this part of like a polynomial here where you're saying, okay, we're also going to multiply two of these terms together. Now it looks pretty innocuous, like it's still a pretty basic function, but the problem is you're basically outside now the linear programming and mixed integer programming world. Those techniques they're not designed to work with the nonlinearities in either the objective function or in the constraints, right? And these things do actually crop up like pretty regularly. Another example might be if you've got a production process and maybe you have two tiers in the production process from raw material to intermediate to output. If your output depends on some property of your original raw input, like say a chemical property of it, by the time you get to calculate the chemical composition of the last part, basically it's going to be dependent on chemical composition of the intermediate part. So you're going to have some kind of multiple decision variables again. And again, you're into some kind of nonlinearity. So there's still options to deal with this. And they kind of really come down to three different approaches. One is to convert the nonlinearity into something linear. The second is to use a convex nonlinear solver. And the third one is to basically forget about the structure of the problem and use a meta heuristic, like genetic algorithms or simulated annealing. Right, so those are kind of the three kind of approaches that are available to you to do that. So in this case, so a quick example for you of using one of the nonlinear libraries. So this actually, and this kind of surprised me because I've been using kind of the heavy duty solvers the last number of months. So Cplex and Garobi and things like that. Which don't actually support nonlinearities. So you have to kind of go to different software for it. I was quite surprised to realize that SciPy Optimize actually handles a lot of these problems without an awful lot of setup. So it's a really fantastic option. So in this case, for example, under the hood, it's using this algorithm called SLSQP, which I have a link to in the notes. But basically what it's doing is it's iteratively turning your nonlinear program into a linear program using quadratic programming. So there are some kind of criteria. So I think each of the terms needs to be twice differentiable and things like that. But actually it does work for an awful lot of objective functions like the one that I just kind of showed you there. So the syntax again is kind of pretty similar to what you get with Google OR. Arguably, it's actually even handier, I'd say. So you can return your objective function. Again, you can use this time, because it's SciPy, it plays really nicely with Python. So you can just use native NumPy here. So for example, you can just, to multiply out your parameters by your value there, you can just use a dot product. So for anyone who's working a lot with ML, you know, done the engineering machine learning courses, you'll have seen a lot of this, you know, dot products of matrices. So again, you can use that kind of representation there, and it's, you know, it works absolutely fine. The same thing with the constraints. So we'll just do that. The only thing about it is the syntax and the constraints is pretty, it's a bit obscure. So you will need to kind of play around with that a little bit. It turns out that the by default, it's greater than or equal to 0 is implied with these constraints. So if you want to get something like I'm looking for here, basically a less than or equal, you need to kind of, you know, get that threshold and then minus your function to get it working. So just a bit of playing around with that, though, I'm sure you'll get to the, you know, the right objective function. It has the concept of bounds as well. So even separate to constraints, you can set a min and max on each of the decision variables, which is quite handy because we know that even looking at it, you know, without any combinations, if we say, okay, we're only going to have one particular item, we know that there's a max on that because we just divide the allowable weight by the weight of that item. So we can come to some kind of bounds on the problem prior to solution there. Yeah, so basically, can we feed in these constraints? We feed in the optimizer, and then all going well, we'll get an output here. So let's play that through. It's going to think for a second because I'm using WSL on Linux, so on a Windows machine. And yeah, so basically it does come out with a solution, and it gets to a value of 40 in this case. I'm just checking something here for debugging. I'm checking if it's overweight by any amount because I haven't discretized this. I basically kind of cheated and used a continuous optimization here, but it's actually come out pretty nicely. It's only overweight by 4 to the e to the 13 or something like that. So for all intents and purposes, for our purposes, it's absolutely fine. That's just kind of a check on it there. So that's the SciPy nonlinear version of the optimization problem we have there. So again, if you are using Google OR tools or PYOMO or Cplex, you won't be able to solve these problems using them. So your options then are SciPy. There's something called CBX opt as well, which is code that accompanies the classic in this field, just convex optimization by Vandenberg and Boyd. They have a really nice library with CBX opt that does this stuff as well. But SciPy is, for me, the last kind of few months have been a treasure trove. So you can solve your MILP ones that you could do in Google, or you can also extend it out into much more kind of interesting problems. The likelihood is that it probably doesn't have the power under the hood for larger problems, because a lot of the solvers, even the open source ones on the market, they're very optimized. You know, the core is usually written in C. They've been around for, you know, 10, 20 years at this stage, depending. So you might run out of road, I think, with SciPy as your problems get larger. But for a place to, a sandbox to kind of work out your solutions, and potentially even for some commercial problems, I think it's absolutely fantastic. So just, yeah, it might be kind of an undiscovered aspect of SciPy that's worth checking out, scipy.optimize. Okay. So yeah, I'm pretty much towards the end now. So if you want to get started with this stuff, I'd recommend Google OR as being a really nice place to start. Scipy.optimize, definitely another really good one. PYOMO, which I haven't gone into today, is probably the best one for production in the sense that it's got a lot of tooling around managing large lists of variables and constraints through indexes and things like that. So really, really nice if you're getting into like enterprise scale applications. The only issue with it is that it's very much its own beast. So a lot of what it's doing is very non-Pythonic, you might say. So it's more around structuring your data. It's more around structuring your problem into a framework for, say, repeatable optimization than just going in and solving a problem. Right, so that's that side. And the commercial solvers, again, obviously very powerful. There's Cplex, there's Gurobi, there's a whole heap of them. Cplex and Gurobi, I think, have nice IDEs as well. So if you want to just, you know, go in and play around with this stuff through a UI, it allows you to do that. The license fees are fairly hefty when you get over a certain number of decision variables. But again, for playing around, you can just download that software, work away with it for free, and you learn an awful lot that way. I think the last one should have put this in the last slide, but just one of the things to recommend, which I've just discovered, is a book called Optimization Methods for Engineering Design by Parkinson, Boiling, and Hendigan. So it's free, it's open source. It's absolutely fantastic because it takes this stuff from a really ultra pragmatic problem solving engineering mindset. Whereas if you get into Boyd and Vandenberg and that stuff, it's really starting from the maths and the theory, you know, very nice to go that way, you know, if you're maths oriented. But if you're much more practically computationally oriented, I'd highly recommend that one. And finally, there is a nice Coursera as well by Pascal Henterich of Monash. It's a bit bonkers as a course. He goes all over the place. But there's two ways you can do that course. One is you can just do all the algorithms from scratch. Basically, generate your own version of branch and bound, for example, in the classic linear programming algorithms. The other way you can do it, if you just want to learn the practicalities of the field, is you can use the APIs. You can use CVXOpt or Google OR and just go through the course that way, and you'll still learn absolutely loads. And then get into the maths more deeply later on. Then if you want to work out step by step in raw Python code. So yeah, that's pretty much it. I hope you enjoyed it. Any questions, just please pop them in the chat, or let me know, and you'll find me on LinkedIn or whatever, and hope to talk to some of you in person, maybe on the next meetings in a few months when things settle down finally. So yeah, thanks very much.